Okay, everybody. Now we're doing some 2.5, and this is basic differentiation properties. And we're going to see that the differentiation properties are very similar to the properties of limits and very similar to the properties of continuity. But let's just do it. So first of all, I want to talk about some notation. Y is equal to f of x. That's our function. This here, this guy up here, that's our derivative thingy ding. And sometimes we were calling that f prime of x. Sometimes we just call it y prime because it's, y is f of x. Sometimes though we call it dx dy, right? Like dy dx, almost like a fraction, or right d dx of f of x. They're just different symbols. Now I believe the reason why do you have such now I understand, between f prime and y prime, that's just which variable you're choosing. But this dy dx thing, well, what's that all about? Well, first of all, you see the connection between derivative and slope because think of d like delta y over delta x. Think of it like change in y over change in x. Only it's d because it's instantaneous. It's not over an interval. And but also I think there's a difference also between because calculus was sort of developed by different people at different times. You had at the same time even you had Newton, you had Leibniz, you had Riemann. You had different people developing in different parts of the world, and they didn't have internet and phones and stuff. So each one made up their own symbols, and they kind of all stuck. So we have all these different symbols. Anyway, so I just want you to. I don't care how you write it. I just want you to know what this stuff all means. And these are just different ways of all saying the same thing. Okay, so if you have a constant, the derivative of a constant is always 0. And that makes sense because constants don't change. So if derivative represents rate of change and constants never change, so duh, Plus the graph of a constant is just a horizontal line. So obviously the slope of the entire horizontal line is 0. There's a lot of reasons why it just makes sense. And that's our theorem 1. Let's go on to theorem 2. Yeah, so you just said blah, 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 blah. So these are all just 0, 0, 0. Whether the power rule. Let's go to the power rule. This is a big one. So we saw in the last section problems kind of like this. We didn't do negative exponents, at least not yet. Actually, we did x to the negative 1 power. So we did that. We did a square root, which is a fractional exponent. We did plain x squared. So we did a bunch of these really in previous. And now we're going to see a rule for any x, the derivative of x raised to any power. And if you notice, the derivative of x squared, if you go through the whole long process, we wind up getting 2x. Had we gone through that whole process for x cubed, you'd have 3x squared. If you go through for x to the 4th, you get 4x to the 3rd. If you go through the whole long process, it's a big pain to do all this, but if you do it, you wind up getting 5x. Now, if you notice there's a little pattern going on here. See, it's 2, 3, 4, 5, and the exponents are 1, 2, 3, 4. It's kind of so. It turns out you may have guessed this that the derivative of x to the nth power is going to be n times x to the n minus 1. And n does not have to be a whole number. N could be a fraction, n could be a negative number, n could be, I guess technically n could even be 0 because the derivative of x to the 0 power, well, x to the 0 power is a constant and the derivative of a constant is 0. So it's going to be 0 times whatever. So, and that's the story. So let's, so the derivative of x to the 25th is going to be 25x to the 24th. The derivative of x to the 5th is 5x to the 4th. The derivative of x to the negative 3, so it's going to be negative 3 times t, I guess, to the negative 4. The derivative of x to the 5/3, well, it's going to be 5/3 times x to the 2/3, because 5/3 minus 1 is 2/3. And that is the story with that. Yeah. Well, this is now, I have 1 over x to the 4th. To do the derivative, it's easier if you write this as an exponent. So I'd write x to the negative 4 and then do it that way. This one here, I'd write x to the negative 1/3 because it's a cube root is a 3rd power and it's a reciprocal. So it's x to the negative 1/3. And this one here, I'm going to write u to the 1/2 power. It's going to just make it easier. And I'm sure that's what they're going to do right here. Right. So 4 4 times x to the negative fifth, which you can convert it back, and you get 4 over x to the fifth. And here we have 1, bring out the 1/2 times u to the negative 1/2, you can write it that way. And this one, the same thing, negative 1/3 x to the negative 4/3, or you can write it that way. Beautiful, yay. Okay, now, suppose you have some random function. F of x is equal to k times u of x plus, in other words, I have a function u of x plus h. I multiply that by some constant, and that gives me a new function, f. So notice if you do go through this whole process, you wind up having an extra factor of k, which can be pulled out, and then even when I put it in the giant fraction, that factor of k can be pulled out. So basically, it winds up being k times this guy here, but this fraction over here is just the derivative of u. So the derivative, so f prime winds up being k times u prime. So f is equal to k times u. F prime is k times u prime. So you could not a convenient way of saying that is that you can pull a constant out of a derivative. And this is stating it, officially. F is equal to ku, so f prime is equal to ku prime. And you can say y equals ku prime or dy dx. These are, again, down here, it's just different ways of saying the same thing. Alrighty. Find the constant times the function. So this is going to be, so here, 3x squared. Well, the derivative of x squared, we know from before, is 3x to the second, 3x to the, I'm sorry, it's 2x. 3 times 2x is 6x. 3 times 2x is 6x. And that's what I wish on all my students. I wish you a lot of success, whatever. Okay, I'm trying to make this a little humorous, do the best I can. So we, where are we here? Y is equal to 1/6 t to the third power. So the t to the third power gives me 3t squared. But 3t squared times 1/6 is 1/2 t squared. How? Y prime is equal to 1/2 times -4 to the negative 4 minus x, so it's -2. Winds up being with a little cancellation, because the 4 and the 2 cancel, winds up being -2 over x to the fifth. And this guy over here, 0.4 over x to the cube root of x, that's 0.4 times x to the negative 3/2. And I'm sorry, the square root of x cubed, I'm sorry about that. And that's 0.4 times this, and then when you simplify it, you get either -0.6 times x to the negative 5/2, or you could say -0.6 over square root of x to the fifth. Either way, you can write it. And that's it. Now, let's go to sum and differences. The derivative of a sum is equal to the sum of the derivatives. And that's what it says right here. And that's really good, because this way, if I have x to the third plus x to the fifth, let's say y equals x to the fifth plus x plus 2x to the fourth plus the square root of x. So I could deal with each guy separately, and then just, if I'm taking the derivative, and then put it into one shot. So the derivative of a sum is equal to the sum of the derivatives. The derivative of a difference is equal to the difference of the derivatives. And but I notice I'm going through this kind of quickly because, well, first of all, you could always replay the tape if I'm going too fast. And secondly, this stuff is fairly straightforward and not that, it's not that complex. And it's just, well, I'm not going to say anything. Anyway, so let's look at some examples. So f of x equals 3x squared plus 2x. So basically I'm going to do each guy separately. So the derivative of 3x squared, notice I took 3x squared and put a prime on it. That means I'm doing the derivative of 3x squared here, 2x with a prime. So that's 3 times 2x. The derivative of 2x is 2 times 1, 6x plus 2, power, done. And they all go the same way. You just do each one individually the way we were trained to do each one individually. Okay. Let's move on. And what about a problem like this? 1 plus x squared over x to the fourth. How are you going to do that? We don't have any. This is like weird. We didn't see anything like this. Well, here's what we're going to do. We're going to take this fraction. I'm going to split it up into 2 fractions. And when that happens, watch what's going to happen. It becomes 1 over x to the fourth plus x squared over the fourth But that's just x to the negative 4, and this is really x to the negative 2. Now I have it in exponent form, so I can just do the power rule, and that's kind of cool and awesome. And power, that's my answer, negative 4x to the negative 5th minus 2 times x to the negative 3, power done. Very beautiful. This matching problem, same thing. I just split into 3 fractions, deal with each one according to the rule of power rule. Okay, instantaneous velocity. An object moves along the y-axis marked in feet so that its position in time, x, in seconds is f of x equals x cubed minus 6x squared plus 9x. Find the instantaneous velocity of the function. That means just find the derivative. So it's going to be the derivative of x cubed minus this minus that. So it's x cubed derivative minus 6x squared derivative plus 9x derivative. And that just becomes 3x squared minus 12x plus 9, power done. Find the velocity at x equals 2 and x equals 5 seconds. Well, all I got to do now, and they mean instantaneous velocity, all I got to do is take 2 and 5, plug it into this new derivative formula, which I just got. And if I take 2 and 5 and plug it into the 3x, not the original function, but the derivative function, x 3x squared, minus 12x plus 9. Plug in 2, I get negative 3. Plug in 5, I get positive 24, and power done. Find the times when the velocity is 0. So all I'm going to do is I'm going to take the derivative, set the derivative equal to 0. Isn't that cool? Because the derivative is 0. Does that mean? Oh, I'm sorry. Yeah, if the derivative is 0, then the function is 0. So plug this. So I'm going to factor out 3. Then I'm going to factor x squared minus 4x plus 3. I get x minus 1, x minus 3, which means when x equals 1 and x equals 3, at those 2 points, the velocity is 0. The derivative is 0, meaning that the velocity is 0. Now, here we have a function, f of x is x to the 4th minus 6x squared plus 10. Find f prime of x. Well, we find the equation of the tangent line at x equals 1. We find the values of x where the tangent line is horizontal. So these are 3 things I want us to do. Well, the derivative, I just, again, do each guy individually. The derivative of x to the 4th is 4x cubed. The derivative of minus 6x squared is minus 12x. The derivative of 10 is just 0, so it just disappears, goes on vacation. Now, we want to find the equation. So this will give us. So we want to find the equation of the tangent. So I'm going to use a point slope. But first, I got to find the point. I got to find the slope. Well, to find the slope, I'm going to take 1 and plug it into this derivative formula. To find the actual point, I'm going to take 1 and plug it into the original function. That's going to give me the x value and the y value, and this. So the f of x, the original function, is going to tell me the y value that corresponds to this x value of 1. The derivative function is going to tell me the slope of the tangent at that point. So, so y minus y1 equals m times x minus x1. So to get the y, so x1 is just 1. They're telling us that. But how do you get y1? Well, you have to take 1 and plug it into the original formula. y1 is f of x1, which is f of 1, which is 1 to the 4th minus 6 times 1 squared, plus 10, which gives you 5. And how do you get m? Well, I just take the derivative now, plug 1 into that, and I get 4 minus 12, which is negative 8. And therefore, my equation now becomes, if I just put it into whatever, it becomes y equals negative 8x plus 13. And that is awesome. And that will be the equation of the tangent line. Now, you know me, I just cannot resist. Let's go. I'm going to graph this, and I'm going to graph that in Desmos, and let's see what magical things happen. So x to the 4th minus 6x squared plus 10. Let's do that first. And then the other function was y equals negative 8x, and I forgot what it was, plus negative 8x plus 13. So let's see if this actually holds up. Negative 8x plus 13. And if you notice, let's pull this down a little bit. If you notice, its tangent. There's a weird tangent because it's a tangent that goes through. That's a very weird tangent. There are times when a tangent actually goes through the graph, which is very weird, but it is what it is. So the tangent at the point 1, 5, that's, there's one. See, if you notice, there's only one dot. There's only one point of tangent. There's only one point of intersection. So that's what a tangent is. And this is one of those weird times when the tangent actually goes through the curve. Usually it doesn't happen, but it happened here. Which makes sense. As I'm coming from this side, you see that's kind of the tangent that way, and I'm coming that side, the tangent's that way. It just happens to be, it's one of the, we're going to get into this stuff more in future sections and stuff, but I just want to point this out. Okay, let's go back. Let's go back now to, oops, that's not what I want. Let's go back here. Okay. So let's go on to the next thing. Alrighty. And I didn't see, what was the problem? What was the question? The question was, find the values of x where the tangent line is horizontal. In other words, where the derivative has to equal 0. So to that, just set the derivative equal to 0. And so I set the derivative equal to 0, which means I'm setting y equals y times, this is the derivative, 4x cubed minus 12x equals 0. I'm going to set it equal to 0. Now, when I solve this, I factor out a 4x, and I have x squared minus 3. So basically, I have x equals 0, negative rad 3, and positive rad 3. I get that from this line right here. And those are 3 places where you would have a horizontal slope. And let's go back to Desmos and see if that looks true in Desmos. So 0. So this would be, that right there is 0. That right there would be, yeah. So here I'm going to have a horizontal tangent. Here I'm going to have a horizontal tangent. And up here I'm going to have a horizontal. So x, by the way, 1.732, if you take a calculator, you'll see that is square root of 3, approximately. And that's negative square root of 3, and that's 10. And if you don't believe me, let's just take 3. Why should you believe? Never believe me. You should never believe anything I teach you. 1.73205, so on and so forth. If you want to be a good mathematician, then you should believe everything I tell you. If you want to be a great mathematician, don't believe anything I tell you. Always work it out for yourself. So that is the story, and that is the end of our fabulous section 2.5. We will see you guys later. Bye. Oh, I have defense against the dark arts now. Bye.